Hello Math 3A and welcome back. We're looking at problem set number 3, examples like these. So you've got things like the chain rule versus the product rule. I'll also do something like this where this is implicit differentiation, logarithmic differentiation, and then after that some related rates. So first of all, with the examples that I made up, like number 1, A and B. So if you look at these two, the difference is this one has an x and this one does not. So this one is the product of two functions, a tangent of x times another tangent of x. But this one is a tangent of x that got substituted into a tangent function. So they look very similar, but they are different. So for this one, this is going to be the chain rule. So you take the derivative of the outside function, and the derivative of tangent is secant squared. So the derivative of this tangent will be secant squared. And whatever's in the parentheses or the argument has to stay the same. So there, I've taken the derivative of this tangent, and it's secant squared. Sorry, my pen seems to be leaking a little bit. Let me try to fix that. There we go. So that's the derivative of this tangent, and then this one stays the same. Then the chain rule says, now you need to take the derivative of what's inside the parentheses, and the derivative of tangent is secant squared. But since this one just has an x, this one just has an x. And we're done with that one. There's no way to simplify it. It's finished. And for this one, we need to use the product rule. Or you could recognize that this means tangent of x times tangent of x. So that's the same thing as saying tangent of x is squared. And then take the derivative of this, first of all, using the power rule. So the 2 goes in front, the tangent of x stays the same, and then subtract 1 from the exponent. So that leaves a 1. And then take the derivative of the inside, and the derivative of tangent is secant squared. And then this one is finished. Okay, then what about like number 1, letter E? So when this has a variable in both places, then you need to use logarithmic differentiation. So just take natural log of both sides. There we go, take natural log of both sides. And then the rule from logarithms is you can take this x and put it in front and multiply. So that's not taking the derivative, that's from pre-calculus. It's one of the rules for logarithms. Okay, now that we've done that pre-calculus part, now it's time to do the calculus part. Take the derivative on each side. So the derivative of the natural log function will be 1 divided by y, and then the chain rule says now you need to take the derivative of y. So multiply with y prime. And on the right side, it's going to be the product rule. So the derivative of x is 1, and then leave the natural log of x alone, plus leave the x alone, and now take the derivative for the natural log of x, which is 1 over x. And then you might be saying, well, you did y prime right there. Aren't you supposed to do x prime right here? Well, y prime is saying take the derivative of y with respect to x. And if you're taking the derivative with respect to x, and the variable's an x, then x prime would be take the derivative of x with respect to x, which happens to equal a 1. So you could technically say multiply by 1, but multiplying by 1 isn't going to actually change the answer, so you could just leave it as the 1 over x. Now all I need to do is simplify and solve for y prime. So for 1, I'm going to multiply this y onto this side, And then I can simplify this a little bit because these x's will cancel, and this is just the natural log of x. And then the last thing is, since I know what y equals, I'll just replace it. So y equals x to the x, and then just put the natural log of x plus 1 in parentheses, and then it's done. And then what about some implicit differentiation? So when I take the derivative on the left side, this is going to be the product rule. So the derivative of x is 1 plus, leave the y alone. Next, leave the x alone and take the derivative of y. So there's the derivative of the x times y. And then for the natural log of y, that's going to be 1 over y. And because of the chain rule, take the derivative. And then it equals 0. The derivative of 5 is 0. And the directions on this one are just find the derivative. And so what I need to do is, this term has a y prime and this term has a y prime. So those two are going to stay on the left side. This one that doesn't have a y prime, I'm going to subtract it and move it to the right side. And then for these two that do have y prime, then factor out y prime. And then that leaves x plus 1 over y. Now to solve for y prime, all I need to do is divide both sides by this. So I would have y prime equals, there was already a negative y, and then that gets divided by x plus 1 over y. Now this is a compound or a complex fraction, so I do need to simplify that. So if I just multiply on the top and the bottom by y, that's going to get rid of that compound or complex fraction. So my final answer is going to be, on the top we have negative y squared, and when you distribute, this is going to be x times y, and this would just leave behind a plus 1. And there is the derivative. Okay, then if you look at the problem set, the remaining problems are about related rates. So a 13-foot tall ladder, and this could just be a board, but what I'm talking about is a straight ladder, not an A-frame ladder, but a straight ladder. So you could just think about this as a board or a pole, is leaning against a house. And so here's the house, and we're assuming that the house is standing upright. If they constructed it well, this is going to be a 90-degree angle. And then the ladder or the board is leaning like this. And because this ladder is not going to change, the length of the ladder is not going to change, then you can use 13. And then the ladder is going to be pulled out, so this is going to be changing. When things change, you have to use letters. So that's going to be an X, and this could be a Y. And then because you have a right triangle, you can do the Pythagorean theorem. So if you have something like a cone, so this is referring to a cone, and this is referring to volume, then you could just ask Google, what's the formula for the volume of a cone? And in this situation, there's the ground right here, and then an airplane is flying at a constant height. So it's basically at a constant height above the ground. And once you read the whole problem and you set it up, you'll be able to make a right triangle. Now, for the example that I made up, that's similar to those. So this is all about a hot air balloon. And this is the ground. The hot air balloon is going to start from here, and it's going to start ascending. And on this particular day, there is absolutely no wind current, so it's going to just go straight up. So that means this is going to be a 90-degree angle. So it starts ascending at 20 feet per second. So this is its height. And because this is changing, I do need to use a letter or a variable. So I'll use height. A person is standing 200 feet from the hot air balloon when it starts. So a person is standing over here, and this is 200 feet. And it doesn't say that the person is running away in fear or anything like that. So that means that this stays the same, so you can just leave it as 200. So how fast is the angle of elevation changing? So one detail that I left out in that is, of course, the person is mesmerized and they are staring at the hot air balloon. They're looking up at it. So this is the angle of elevation. How fast is the angle of elevation changing? So this part, how fast, means derivative. The angle, so this part is saying find the derivative of the angle. Or if you want to be more precise, it's the derivative with respect to time. So this is then saying when h is equal to 100. So basically we need to use this picture twice. One time when this is just a variable, and then also one time when the h becomes 100. So looking at this triangle, because it does involve an angle, that's a good time to use trigonometry. So this would be opposite and adjacent, so that would be tangent. So tangent of theta equals the opposite over the adjacent. Now what I can do is I'm going to have to use this equation twice, one time to plug in the 100, and then another time to take the derivative. So I'm just going to do the trigonometry part right here. So if I plug in 100 for h, that's going to be tangent of theta equals 100 divided by 200. And that means tangent equals a half. And if you do tangent inverse of 1/2, then is that like pi over 6 or something? Let's see. So if you divide that by pi and ask the calculator what fraction that is, it says it's not a fraction. So that means we just need to use this 0.464. So theta equals at 0.464. Okay, so we'll use that in a moment. We now need to take the derivative. So the derivative of tangent is secant squared. And then the chain rule is going to insist you take the derivative of this theta, so that's theta prime. But that's actually good news because that's what we're supposed to be solving for. And then on the right side, because this is just a number, you don't have to use the quotient rule. You can just say take the derivative of h while the 200 stays there. All right, next up, the balloon was ascending, so going up at 20 feet per second. So this right here is the h prime. So we know that the h prime equals 20, and that the theta equals the 0.464. So I can plug those in and then solve for the theta prime. So this is going to be secant squared of a 0.464 times theta prime equals, and then this is the h prime, 20 over 200. And then of course, this reduces, so this is going to be 1 over 10 on the right side. And then this actually means 1 over cosine. So 1 over cosine squared of the 0.464. And then I already reduced that, so that's 1/10. So then to solve for the theta prime, just multiply both sides by this cosine squared. It will move it over here to the top and say cosine squared of the 0.464 is divided by 10. So cosine of the 0.464 get squared and divide that by 10. So the angle is changing pretty slowly at a 0.080, and then this would be in radians per whatever the unit for time was. And that would be per second, radians per second.